Today we have Robert here, who is a student, a PhD student at Caltech. He is working with, I guess, Thomas Biddick and John Preskill. And recently he did some work with Google on power of data in quantum machine learning. Quite interesting work. In past, Robert has also visited CQT, and with Patrick, like we did some work in the past. He's quite good in quantum machine learning and these topics, and he has been exploring it for a long time. So today it's a privilege to like invite Rahul, Robert for the talk in the Quantum Machine Learning Journal Club. Robert, the floor is yours. Like, please proceed. Yeah.
Okay. Yeah, thanks for having me here. I'm Robert, and this is a joint work with people at Google AI Quantum, where we try to explore how the presence of data could change the power of classical ML so that it would impact quantum ML. So the title of this talk is called Power of Data in Quantum Machine Learning. And here's the archive link. So basically, before going into quantum ML, one thing we wanted to understand for this work is how powerful are classical ML models for quantum problems. And as we have already seen, there has been a lot of works that try to use classical ML to solve certain challenging quantum problems. For example, in quantum chemistry, people have trained graph neural networks to predict property of a molecule that results in like 10 to the 5 times speed up. And in quantum physics, people have been exploring solving ground state of local Hamiltonian using like restricted Boltzmann machine. And of course, there's also other natural sciences, like people have been using classical ML to do weather forecasting and simulating like some chaotic behavior that results in like billion times of speed up. However, all of these works are mostly heuristic, like they just look at these kind of problem and they just apply some standard classical ML technique and then just try to see if it works and how well does it work, etc. But here we wanted to understand a little bit more than just that. So as you can see, classical ML have been so useful, but where does this kind of power come from? Why are classical ML seemingly more powerful and results in a lot of speed up over traditional classical algorithms? And to try to answer that, we consider a more rigorous kind of perspective. So you can think of machine learning algorithms. People often say AI and so on. But basically, it's just a normal classical algorithms, but with the ability to learn from training data. So the only additional part is the training data. So if you don't have any data, then this is just a normal traditional classical algorithm. However, when you have this data, it changes the sort of the complexity of the things. So in the following way. So when I say training data, I refer it to a set of information of the form X mapping to Y, where X is like the input, while Y is the output. For example, in decision problems, X is some bitstring and Y is whether X is in the language or not. So now, how do you think of classical ML in terms of this more computational complexity kind of setup? So first, in the left-hand side, we have a normal classical algorithm, BPP, where for different input size, different problem size, you have the same Turing machine that solves the problem. In the intermediate, we consider this classical ML algorithms as being normal classical algorithm, but you have this additional training data that allows you to take advantage of it, to learn from it. So here you can think of it as a polynomial size set of input-output pairs, given as examples, such that you can learn from it. So you can also compare this classical ML class with P/Pauli, which is basically the same, like it's classical algorithm, but you have this additional advice string, which is just a bunch of 0, 1 bit string of polynomial size that you could utilize to improve your ability, your computational ability. And you can actually think of this training data as a restricted format sometimes. And that's where the computational power comes from. So yeah, and basically our first claim for this work is that this intermediate class, this class of our classical algorithm with the ability to learn from data, is a strictly larger, would be able to solve a strictly larger complexity class than PPP. So that means there are problems that's not solvable by classical algorithm, but solvable by classical ML algorithm with data. So there's nothing special about learning. It's more of the fact that you have data that you could build upon. So to illustrate this kind of fact, we consider the following example. So let's say we wanted to be able to, like, given some quantum state input, let's say here it's a single particle unsight fermionic state. And by that, it's basically means that it's a superposition of one, like kind of like here's an example, like if n equal to 3, then it's a superposition of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So in this case, you have this psi neat, and what you wanted to do is, let's say, like simulate the evolution of this input or predicting some property after the evolution. So for in this case, let's say the unitary U is the particle preserving Hamiltonian evolution. In this case, if U has satisfied this, then you can think of it as just an n by n unitary transformation, because since it's particle preserving, it would always take states, like single particle states, and map it to single particle states. So after you apply it on psi neat, you would always be in the same subspace. So this is very easy to simulate classically because it's just like a small matrix multiplication. On the other hand, if you consider this unitary U to be a general interacting Hamiltonian, so it's not particle preserving anymore, but it could create particle and so on. So in this case, it would be able to explore the entire 2 trillion Hilbert space. And in such a case, simulating this evolution U applying on psi neat is generally going to be hard because this U is just a general quantum circuit. You can think of it that way. So when you apply U to psi neat, now it wouldn't just lie in this single particle sector, single particle subspace, but it could explore the entire 2 trillion Hilbert space. So the resulting state would be a superposition of all the 2 trillion computational basis state. And similarly, if you wanted to predict some property, like some observable expectation value for the output state, U acting on psi neat, it's also going to be hard. It's also expected to be hard classically, because if you could do that efficiently, then you could simulate basically all quantum circuit. However, for this particular task, it's actually very easy if you have training data. So by that, I mean, suppose you have examples of psi init mapping to, like, this different psi init taking as input, mapping to its corresponding property, psi init U dagger O U psi init, as a real number. So if you have those training data, then suppose I give you a new psi init, it's actually very easy to predict what this outcome should be. And to see that, you just noted that whenever you take this expectation value, you can write it out as a huge quadratic form with exponential parameters. But equivalently, you can also write everything in the original subspace. So it would just become a quadratic function with on an n-dimensional vector space. So in that case, given this training data, all you do is for example, you use a quadratic kernel SVM, like you just try to learn a quadratic function. And after you successfully learned that, when you're given a new psi neat, you can just easily predict what that output is. So this is a pretty simple, but also kind of illuminating example, saying that when you are given data, then computationally things would change. But more rigorously, we can consider the following. We can just immediately define, we can just directly define what this complexity class is for a classical algorithm with data. And we consider the following. So we say a language L is in this complexity class if the following holds. So first, there exists a probabilistic Turing machine M. So this M here is basically the classical ML model. So what it does is it would take an input X of size N along with the training data. So normally it would just take an input without the training data, but now we assume that it could learn from the training data. So it would also take this training data of polynomial size, where this xi are sampled from some distribution, dn, over all inputs of size n, and yi is equal to 1 if xi is in L, otherwise yi is equal to 0. So important thing to note here is that this training data is randomly sampled according to some fixed distribution. So this dn has to be fixed compared to the input. I mean, it's fixed according to the input x. So you cannot just select the training data along with your input. It's kind of like a separate thing. And after defining this, you just say that the following three things hold. First, it has to run for polynomial time on all input. And second, for any input x, it would output 1 with high probability in language. And if x is not in the language, then it would not output 1 with high probability. So this following part is just the same definition as BPP, and everything pretty much the same except for this availability of training data. So first of all, what you could easily show is that you can use a similar proof at Edelman's theorem to show that this complexity class is contained inside P/Pauli. So P/Pauli is the class where you have a deterministic Turing machine runs in polynomial time, and it could take a polynomial size advice. So it's a little bit different, but you can de-randomize the training data, and this is what you would get. So you know that this classical ML class is not that powerful. It's always contained inside P/Pauli, and it's likely strictly contained inside P/Pauli. Yeah, so just to recap, P/Pauli is just classical algorithm with advice strings. And another way to view P/Pauli is as classical algorithm that have unbounded pre-computation time. And by that, we mean every time you wanted to solve certain problem up to size n, you first do a bunch of pre-computation, and after that, you start taking input. So now we know that classical ML algorithm is contained inside P/Pauli. We also wanted to know how does it compare with BPP. So actually, it's quite simple. The following thing I would show is actually super straightforward. Basically, first, you know that it definitely contains BPP. And second, you know that there is a simple and rigorous separation between BPP and BPP with training data. And we give the following example. It's a little bit complicated, but actually it's just to illustrate the point of what classical ML could do. So let's say we have a hard language, L hard, which is basically just an undecidable unary language. And let's say we consider another language, L easy, which is some easy language that's inside BPP. So you can solve it with traditional classical computer, like classical algorithms. And now we consider the following class, kind of like as a XOR between L easy and L hard as follows. So for every input size, if you found that 1 to the n is inside L hard, then you just take the same thing as L easy. So like you take every x that's inside L easy with size n. However, if you found that 1 to the n is not in L hard, then you take the complement of L easy for that input size. So I hope that makes sense. So you define this language, and now what you could easily show is that using just one training data point, just sample randomly, what the classical ML algorithm would be able to do is, after seeing this training data, it just check if x0 is inside L easy or not. So by doing that computation, it would be able to know if 1 to the size of x0 is in L hard. And by getting that particular information, so basically you have this one training point, you use the training point to gather some like hidden information, and use that hidden information, you can immediately generalize to any input x that have the same input size, x as x0. So by definition and by construction of the classical ML algorithm, you can see that this language L is inside this classical ML algorithm complexity class. And I talked with Thomas Biddick, and he told me to name this complexity class. So we ended up deciding to call it BPP/SAMP because it's basically BPP, but you can have sampled training data that could boost your computational power, similar to how advice could. On the other hand, this language L is still undecidable because there are some portion of this language, this L hard thing is undecidable. So this language L is also undecidable as long as this L easy has for different input, for every input size, it has a it has some inputs that's inside L easy and some input that's not inside L easy. So it's not hard to see that this L is also undecidable. So it's definitely not in BPP. So by just doing this very simple argument, you can get the following kind of conceptual idea for how all these different classes were related. So first you have the normal classical algorithm BPP, and then you have a bigger class BQP that contains BPP. On the other hand, you also have P/Pauli. Because it contains undecidable problem, it would be outside of BQP and actually outside of all decidable languages. And similarly, we have this blue class, which is classical ML algorithms with data that would be contained inside P/Pauli, but it would be bigger than BPP. And it's likely that it would contain problems that's not in BPP, but in BQP, but it would also contain problem that's completely outside of both complexity class. So if there's any question, please feel free to ask. So after talking about this, what it meant was there are actually two implications from this. The first one, which is not really, I'm not going to cover here, but John Praskell, Richard Kuhn, and I are writing a paper that discusses this, is how you could train classical ML algorithm to solve some quantum many-body problems that have there's no classical algorithms yet now that could solve the same problem. So we are trying to explore that. So basically, because there's more power in classical ML algorithms that could learn from data, first of all, it's possible that you could solve certain challenging quantum problems, like finding ground state or things like that, by learning from data. So it's very important that you have the ability to obtain some training data, let's say by doing some physical experiments to boost yourself. So originally, this data, you cannot simulate it classically, but you could still do physical experiments, get the data, and then train your classical model to make it solve more problems. And another implication that would be mainly explored in this work is classical ML algorithms could sometimes rival existing quantum ML, even for learning some quantum models. And yeah, so that's basically what we are going to focus on, and let's dive into that.
So like Robert, just for clarification, like so the classical model with data basically just means that you have some training data which you have obtained, and with advice basically mean that you have done pre-computation on that to get the advice or something. I mean, how are they different? Like,
so here, so advice is basically just a bunch of bit strings that could be anything that's given to you. And then you just use the bit string to do whatever you want to solve the problem. On the other hand, the training data are examples. Like it's telling you that this input corresponds to this output. So it's a more restricted version than advice, because advice could be arbitrary. It could just be like a bunch of zeros ones that is given to you to maximize your ability.
Okay. Mm-hmm.
I hope it makes some sense. Yeah, but just by building on top of that insight, we are going to talk about how this could impact and how we could understand the potential quantum advantage in learning problems, or the lack of potential quantum advantage in learning problems. So the main thing here is that people often expect that you have some deep quantum neural network, or you have some classically hard quantum kernel function. Then you would have some quantum advantage in machine learning. But that's basically not true, because you might have these kind of data that could boost the computational power of classical ML, such that it could cover a little bit of like some part of quantum problems that could be, that's originally not classically simulable. So that's
but then there is this extra cost of obtaining the training data, right?
Yes, yes, that's true. So obtaining training data could be complicated. However, for machine learning problems, you already assume that the training data is there. Okay. You already have the training data, and then you try to use the training data to predict well. So the training data is there originally, and that's what we're going to focus on. But for like the first task, if you wanted to use classical ML to solve some quantum many-body problems, like ideally you just don't need any data, and then you could just have a classical algorithm that could do it. However, maybe it's too hard. So then you might want to resort to obtaining some data by like doing some physical experiments and then generalizing for other part. But that's not going to be covered in this talk.
I mean, I would say like similarly, when we talk about rival quantum algorithms, like there also we should compare it with like quantum algorithms with data. Like
yes. However, yeah, there's one thing that's missing I didn't talk about. So the reason that it could go outside of BQP is because the data is outside of BQP. However, when you do things like you assume that nature operates quantum mechanically, then all your data is simulable by quantum computation. So your data would be inside BQP. And in that case, this blue thing would not be going out of this quantum computation, but would still be within this. I hope that makes sense. Yeah, so basically we wanted to understand when would existing quantum models be void of quantum advantage, and what kind of property is that? So in this work, we focus on quantum model that is given as the following. So your input x is just some classical vector. You encode x into some quantum state rho of x. Let's say like just a pure state. And then what you would do is you would apply some unitary evolution onto this rho of x. And after applying the unitary evolution, you measure some observed. So that's the quantum model we would be thinking about. So basically, it's a model that takes in classical vector and produces a real number as an output. And this also corresponds to basically all the computation that you could do on quantum computer, since it's very general. And in particular, in quantum machine learning, this quantum model contains two of the most studied models. The first one is quantum neural networks. I think it's quite obvious for quantum neural networks, because in quantum neural networks, you get this input, you embed it into some quantum state rho I, and then you apply some unitary evolution, which you call the quantum neural network, although it's basically just a unitary. And then you take you measure some observable to get the expectation value on the evolved state. So that's pretty much the same as the quantum model we defined here. However, another one that's more recent is quantum kernel method. In this case, you embed your input xi into the quantum Hilbert space. So the first step is the same. But afterward, what you do is you train a kernel method. You train a kernel method with a kernel function defined using the quantum Hilbert space. So you can think of it as just a kernel function as like a similarity measure between different input. And yeah, and here what quantum kernel method does is you just embed the inputs into the quantum Hilbert space, and then you use the native geometry for the quantum Hilbert space to define the inner product. You just take the inner product between two quantum states to define the kernel function. And this is a method that's proposed in in several works. There are some works by Maria Schut, and also there's this work from IBM that was published last year in Nature that study like propose this and study how it works. And why this quantum kernel method also falls into this framework, like fall into this definition of quantum model, is because of the following useful fact. We've proved the fact in our paper, so you can see it's very easy. Basically, this fact just says that training a quantum kernel method is equivalent to training an arbitrarily deep quantum neural network that matches any observable at the end. So there are some tight connection between quantum kernel method and quantum neural networks. Basically, when you're training quantum kernel methods, it's pretty much the same as training quantum neural networks, but like a huge quantum neural network. So yeah. So that's why it's also contained in this quantum model that we discussed. And we also focus on particular class of machine learning models that's given as follows. So here we would consider the training data to be given as like xi, mapping to the observable measurement. So I'm just assuming that some quantum model is the true solution to the problem. Like the underlying function is some quantum model. And now we can obtain some training data from it. And then we wanted to train a classical machine learning, like a classical neural network, to be able to predict what this quantum model would output. So like you have some quantum neural network that you have designed, and now you wanted to know if a classical neural network could actually just mimic that quantum neural network. And that's kind of the setup here. So in particular, we focus on training classical neural network with large hidden layers to minimize the following function. So the second term is just a least square kind of loss, where you say, I want the output of the classical neural network to be close to the training data, like the output for the quantum model. So we have the second term here. And then we also have the first term. The first term basically regularizes this classical neural network, which means that you try to design R function, this function, as in a way such that certain classical neural network F would have a larger value R of F, basically meaning that this classical neural network is like maybe it's too complicated, so you penalizes it. This is quite important in practice to prevent overfitting, because you don't want your model to just fit the training data completely and have no generalization error. So you have to have the first term to control that, and then you have the second term for minimizing the training error. So let's say you consider this following setup, which is pretty natural and covers a lot of different classical ML models that people consider. One could easily, not easily, but one could show that the trained function f, so after you minimize it, and then you will find that this function f would be equal to this formula here. So you can see that what it's doing is, what this part is doing, it's generalizing the training point. So like kind of like first you embed xi into your quantum state space, and now that's rho of xk. And what this is doing is it's generalizing from your training point to a new point. So this x is some new input, and what it's doing is having this nonlinear formula that would, you place x here, and that would also depends on xk. And naively, you can think of it as like, let's say xj are close to xk, then this kernel function would be large. And that's okay. Let's assume that if xj is, like it depends on how you define the kernel function. But if xj is close to xk, if xj close to xk result in very large k, while when they are far, this kernel function is small. What would happen here is basically this x would just look at the closest points and then try to interpolate, like, or extrapolate from the quantum state for these closest point to this one. So that's basically what this formula is. And then the rest is just you take the U dagger OU on the interpolate, like the extrapolate, like the interpolated state. And that's what the trained neural network would actually be. One could show that. One could show that this is what it would be. Using some of the framework that people have developed called neural tangent kernel, you can show that if you train a classical neural network with large hidden layers, the resulting function f of x would be given.
May I have asked a quick question?
Yeah, sure.
Would that mean that we already have the analytical form for f of x given the data?
Yes.
Then in practice, why would it still be necessary to train your network given that like we already have the analytical form as you just show us?
Right. So this is because oftentimes in practice, you might want it to train classical neural network not with large hidden layer. Like maybe you wanted to restrict it so that it's like the hidden layer would only have like 50 neurons rather than like a large number of neurons. In those cases, when you have finite kind of hidden layers, like small hidden layers, you don't have an analytical form and you have to train the model.
Mm-hmm.
Yeah,
And
so that's
otherwise, if I just want to do it like with the large hidden layers, I can just use this expression and there's no like any expensive computational cost, right?
Yes, no, you can just use this. Although if you look carefully here, you have to take the inverse. So taking inverse also takes time. So it's not like it's free.
Okay.
Yeah, and it might be the case that when you actually just train it, it's more efficient than really taking the inverse. So that's another thing to keep in mind. And actually, there are already software package. Like Google also have a software package called Neural Tangent that basically does exactly this. So they would compute everything for you. Yeah, so these are the sort of the machine learning models that we would consider. And note that there's a very important thing. So if you have like a convolution neural network, or you have like a graph neural network, or some V4 neural network, different forms of neural network, they would correspond to different K, the similarity between X and Xi. So you can think of a neural network as basically a way for defining what kind of classical inputs are close to one another. So this is a class of things, of ML models, not just one ML model. So and furthermore, this same formula also works for like more traditional ML models like kernel SVM. If you train a kernel SVM, you can also write down the explicit formula like this, and just with some other K. So oftentimes people use Gaussian kernel, which is basically you take the two norm between X and Xi, and you put it on the exponent with a minus sign. This also holds. Yeah.
I would also ask a question on that. So the example of the SVM, so the kernel, usually you choose it, right? Like you said, yes. you can take the Gaussian. So what exactly does the training in that case? What are you training with when you do the normal training? Do you change the parameter in your K, or what is it?
No. Yeah. So actually, like in every cases, even without analytical forms, when you have a training data and when you properly define the model, you can always write down what this model is, right? Like the trained model. So this f of x here is the trained model. So you already trained it. It's just that in this case, you can write down the closed form of this. And yeah, kind of like when you have a neural network and you don't have all the weights, like all the weights in the middle are like randomly initialized. And then what you do is you start training it. You say, for this xi, I want to have this trace thing as an output. And then you would do like back propagation to try to optimize the weight such that your neural network could train on the training set. And after you train it, this is the closed form solution that you will get.
So I guess, okay, maybe I was not clear. So for a neural network with backpropagation, so you have the form, you're gonna have the matrix multiplication, the nonlinear function.
Oh, no. So this is yeah. So you should first forget about this and think of the normal classical neural network, which is just like you have X, and then you have some linear layer, and then you have activation layer, and then you have linear layer, and so on. So that's what you get. And all these linear layers are parameters that you need to train.
Yeah, so that's what I mean. So you have this form, you have this linear and nonlinear, and then the training is that you're going to train the coefficient in your matrix. So yeah, exactly. Yeah. So my question is that in this form of f of x that you're showing here, what are the parameters? Where are the parameters that I should train?
Yeah. So what I was saying is, first you have this classical neural network with a bunch of parameters, and then you would start training it, and eventually your training would end, right? Like you try to minimize the optimization problem, and then you found the minimum, and then you stop. This formula here tells you what is that point when you stopped. You can write down the entire function, the function after you train all these parameters.
So Robert, I could gather basically what you were saying, that the final hypothesis that I get from the set of basically we are searching some hypothesis from a set of hypotheses, right? And the final hypothesis that we get from by training the neural network, I can represent it. Yeah, I can represent it as some kind of a kernel function, like using some kernel function. I can represent it. But still at the level of representation, you are saying that there is this equivalence, but at the level of trainability, still because they could correspond to the landscape where you are training could be different in the two cases, and they may not be equivalent, right? But the final.
So actually here the thing that's happening is, if you have large hidden layer, there would be no local minimum, and there's only one global minimum, and that's this.
It's beautiful.
It's a pretty nice result. And
I mean, for neural network, like you're saying that it's you can get this by construction create a very nice landscape.
Yeah. You can see like for example, the second reference that I cited is that's convex neural network. So it's actually convex. So when you have large hidden layers, it becomes convex. Beautiful. And you can always go to kind of the minimum, essentially. And that's why you can write down the form and then reason about what it's doing. So now the next question that we wanted to know is, suppose we have a quantum model defined by X, embedding into rho of X and measure U dagger OU. And we have another machine learning, and we have some machine learning model. And if you look closely, all that matter here is kernel function K. So if you define a different kernel function, it corresponds to a different machine learning model, right? So basically you can think of it as a machine learning model just defines the geometry between input. So how close are they between different, you have this image corresponds to dog, this image corresponds to cat, how close are they? And that's sort of the geometry that's being defined by the machine learning model. So now, in order to understand if this machine learning model could learn that quantum model, we have to look at this this form here, which we define as SK. SK is basically equal to the trace of A times U dagger OU tensor U dagger OU. And this tensor A is basically this form. It's the sum. So IJ is over all the training data. So you can think of it as you have all the training data corresponds to different points, and now using the machine learning model, you define how close are different points, and the quantum model defines the true function that maps different points to some real number. And you can define this quantity, it's a real number quantity, and it's also a positive number SK, as follows. And what you could...
Robert, can you sorry to interrupt, but could you go back to the previous slide where you were talking about the convexity argument? So basically, it's convex with respect to, I believe, the parameter landscape, right? And with respect to the parameters. And you have some loss function. So basically the minimum will be unique with respect to, but the but the minimize, there can be many minimizers, right? I mean, or do you have uniqueness of the minimizer also? Because what you are writing is the minimizer, right? I mean, you are saying that the
Yeah, this is a minimizer.
so is it unique, or like, or no matter what minimizer you have, like each of them can be like always written in this neat form, or it doesn't matter, right? Because yeah, I mean, you just
it's always a unique form. It's always a unique form. Okay. So that's the interesting part of it. Mm-hmm. And basically, what I'm going to say here is that you can define this quantity called as k, where this a is kind of like this term that's the inverse. Like you take the kernel matrix, you take every 2 points, create this n by n matrix where n is the size of your data, and you invert it and you define this whole thing. And then you take the trace of A with this quantum model, U dagger OU, tensor product with itself. This is always going to be a greater than equal to 0 value. And the crucial point that you could prove is that if you found that this quantity is small, then the ML model would be able to predict the quantum model well. So it's like a generalization error bound, saying that you can just evaluate this quantity, and if you found that it's small, then with high probability, it's going to be able to predict the new inputs accurately. So to visualize this, here is a plot for this whole thing. Basically, different ML model, you can think of like a convolution neural network or a feed-forward neural network. They correspond to different kernel function k, so like k1 or k2. And for different kernel function, they induces a different. Actually, you can look at it and it's kind of like it's basically a squared semi-norm. So it would induces a different quantity as that's basically a squared semi-norm. And what I mean by that is kind of like a norm. It's basically norm squared. So what it corresponds to is for a different ML model, it creates this kind of geometry shape on the space of all quantum model. So for example, you have different quantum model corresponding to different observable or different quantum circuit, like U1, O1, U1, and or U2, O2, or U3, O3. You can visualize what I was just saying using this plot. Basically, for like ML model 1, let's say it's a convolution neural network, you have this kind of a ball that's going to define a number for different quantum model, like let's say quantum model 2. For example, yeah, you can visualize it as, you can think of it as just like this kind of ellipsis with like that's becoming larger and larger if the quantity S becomes larger. So let's say like you have quantum model 2 that lies within the center. That means its S quantity is small. Then you know that it's going to be able to predict quantum model 2 well. On the other hand, like for example, quantum model 3, because it's out in the outside in the outmost norm ball, you know that it's going to predict worse. Like when you use this ML model to try to learn quantum model 2, it's going to predict well. But if you try to learn quantum model 3, it's going to predict worse than quantum model 2. And basically, when you have different ML model, they correspond to different kind of geometry on the quantum model that you could learn.
Just a quick question. Is there any physical reason why it has to be ellipses here?
No. It's not ellipsis.
Okay.
But I'm just it's just a visualization. So you can think of it as just some other norm space that you could create. Like maybe it's like a diamond or like a square or some other things that could be very complicated.
Okay, thank you.
And this is not just like I'm just saying things. You can rigorously.
Sorry, may I ask you something in the previous transparency?
Yes.
Am I correct in saying that what you did with the K kernel is what is a Gaussian process?
Yes, it's actually very related. Yes.
So
you can think of it
you are setting up what the Gaussian process is, which by using inference, you train in an exact way. That's why you have an exact formula if the intermediate layer is very large. Okay.
Right.
So the key idea, am I correct? Yeah, this just the one before, yeah. the one before transparency. Yeah.
Oh, you mean this one?
Yeah. The second formula is the training of a Gaussian process. Okay.
Yes.
With
yes.
errors and everything.
Yes.
So the key idea is that you are mapping the quantum algorithm to a Gaussian process, and you are telling us when this is possible. No, am I correct?
Right. Right.
So the next
but actually, you can always have this.
Yeah.
It's just it's not going to predict well. Like when you have this Gaussian process and then you fit it, you train it, and now you create this Gaussian process, and then you wanted to know whether it fits well with the true quantum function, the function generated by the quantum model. And this SK is the quantity that quantifies this.
Yeah. So the key idea then in the next transparency is that if this, no, the previous one.
Sorry.
No, the next one.
See.
Yeah. So here is the key idea, no? That if this A is small, then everything matches to a bona fide Gaussian process. Is that the key idea?
I think that's one. Yeah, that's one way to think of it. Yes.
Though in general, it may not be mapping. It may need.
This could be large. Yes.
Yeah,
that it could be large.
So you're telling us that there are a set of quantum problems that may be amenable to the Gaussian process philosophy.
But it also depends on how you define the kernel in your Gaussian process, right? So.
Okay, thank you. And this, and the next transparency, the one before, is that also this understood as this mapping as a feature map?
Yes, yes, this phi is the feature map. So. So this K could also be quantum ML, like a quantum kernel method.
Okay.
So that's why we are going. That's what we're going to talk a bit about. So you can use it to compare between different like classical ML with like quantum ML and so on, using this kind of picture. I hope that, yeah. And basically, yeah, this is a rigorous formula for the rigorous statement about this thing. So suppose you have some training set xi mapping to yi, and yeah, and then you try to train a ML model with the corresponding kernel function k, then you know that, let's say this g of x is the model that you finish training on the training data, then this g of x, like in the expected prediction error, the expectation value of g of x minus the actual quantum model would be less than or equal to this term plus this term. The second term was just like some Gaussian fluctuation with some probability, but the first term is the crucial one, basically telling you that you want this SK to be much, if this SK happens to be much smaller than your training set, then you will predict well. Okay. So here is an illustrative example. So let's say you use the quantum kernel method proposed in the supervised learning, and there's also another recent work that shows a rigorous and robust quantum speedup using quantum kernel method. If you consider this type of method, which defines the kernel function, the geometry, using the native quantum Hilbert space, then you could write down a precise sort of a, you can write down what this SK is. And there is a pretty tight upper bound that basically states the following. So you will see that if you train a quantum kernel method, then the prediction error for learning some other quantum model, like some other quantum neural network, would be less than or equal to this term, where the middle part, this minimum over d and trace O squared, is the SK that we discussed before. And what this d is, this d is the dimension of your training set quantum Hilbert space, which could be huge. And the second part is the squared Frobenius norm of the observable O. So let's say your observable O is a local observable, then trace O squared would be exponentially large. So what that means is, even though quantum kernel, like training quantum kernel method is equivalent to training an arbitrary deep quantum neural network, its generalization performance is not great. And two factors significantly determine its performance. The first is how big of your quantum Hilbert space do you embed your input in? If you embed your input in the in a very separated fashion that everything is very far apart, and then your quantum model is like measure some Pauli Z operator in some qubit, then this generalization performance is going to be bad. You're going to see that quantum kernel method actually fails. However, if you found that this trace O squared is like 1, and then the dimension is not very large, then the prediction error would be small. So it predict well. So this is just one illustrative example. And another important thing based on this framework is you can use it to understand the geometric difference between two different ML models. Because as we have discussed, for one ML model, it creates this kind of norm space. And then for the other ML model, it creates a different norm space. And we all know that the two different norms, you can relate it using some geometric constant. Like for example, L2 norm and L1 norm could be related through square root of dimension. And here we can also relate between two different ML models. So what you could show is the following form. If you define this G, a divergence between one model and another ML model as this form, which would always be greater than or equal to 1. Then what you would find is that this SK1 would always be less than or equal to G squared times SK2. So the way you think of it is kind of like you look at the unit ball for ML model 1 and you try to find a point that's largest compared to, or another way to say this is you look at the unit ball for ML model 2, SK2, so this is equal to 1, and then you try to find a point that has the largest SK1. So that's the definition of this G, and you could write it down explicitly, you could also evaluate it practically, and so on. So why this is important? The first one is it says that suppose you found that this G constant is small. What that means is that these two ML models are highly related in the following sense, is that the first ML model, K1, would always have a similar or smaller SK compared to the second ML model. And the importance of this is the following. So suppose you compute the geometric difference between a classical ML, like some convolution neural network, versus some quantum kernel, like the quantum kernel method. If you compute that and you found that this G constant is actually very small, what that means is that classical ML will predict similar, like maybe slightly worse, but similar, or better than quantum ML for learning any quantum model, which means like you don't see any advantage. So this criteria is kind of strong. And it's also what we will show in the experimental section. I might need to just go directly in there.
So,
Otherwise,
Robert, so like while like I'm trying to understand this geometric quantity GCQ, like or like I mean in general, like to relate two different models, like I mean, so it's defined in the model space, like you are in the model space where like each of the models are some hypothesis class, and you are trying to find some kind of distance between the hypothesis class by doing some functional analysis or something.
right, but another way to think of it is it's every ML model, like the ML model we consider here always has a corresponding kernel. And this kernel defines whether 2 points are close or not. And you will have two different models that have different ways of defining things. And basically what I'm saying here is that you can look at that geometry and say like, how far are they? If they are not very far, then you will not see much advantage, even in learning any quantum model. So that's the sort of thing.
But this argument only apply if you can define the kernel of your model, right?
Yes. So if you don't have an associated kernel, then this thing doesn't really tell you much.
And
So that,
what you said is that for every like neuron network, even with the finite layers, there is a kernel associated with it.
oh no, only with large hidden layers. Only with large hidden layers, there's a kernel associated with it. Otherwise, it becomes very complicated. Like the landscape becomes weird. You don't know if you, like every time you train it, it becomes different things. And then you cannot really say much about the performance.
Okay.
Right.
So in other words, you need this closed form that we discussed few times already. So that when you can write this closed form, then you can derive this S of K, and then you can look at this
Yes.
G.
Yes.
So all the time you need this model that you know the exact, like it's a convex optimization problem at the end. You know the final solution. There's nothing in terms of like training or local minimum.
Yeah, because local minimum, yeah. Then you can't really argue about things there because the dynamics become too complicated.
So I think that's why I got, okay, sorry, I don't want to take more of your time on this question. I'm going to be very quick, so I don't want to be stubborn. But I think this is why I get very confused with this closed form. When I look at it, it seems to me that there's nothing left to define. It's like I can define my K of X, I can define the kernel, so I can have this gram matrix, so I can have this exact form. So there's no training left. I'm very confused about the machine learning part in this closed form.
I
because I would always use this form if you tell me that this is exact. Why I would use anything else? There's no training. I have K, I can find a solution. Done.
Yes. But note that, so the thing that I just mentioned was actually very recent theoretical ML development. And they actually found that if you just use that form, oftentimes they compete with some of the finite, like normal classical neural network that people are using. You just use that form, and then the performance is pretty much as good in various cases.
Okay, so it means that if you would have infinite or very large neural network, you have this limit of convex function. This is the solution, and I could use that all the time. But sometimes for smaller, like doing the exact training is actually more efficient, and I get also good solution. Is it what you're saying?
Right. You doing this, yeah.
Okay.
Yeah, but yeah. So okay, so this is not just bad news here. Like it's like when you found that G is small. Okay, so if you found that G is small, that's bad news. You're not going to see much advantage. On the other hand, if you found that this geometric difference G is large, then by sort of by definition of this G, or sort of by construction, there always exists a data set that satisfies this equality. So remember that what we had before is like, okay, this one. It's like S is always less than G squared times S2. And this inequality could always be saturated. So that means there always exists a data set such that SK1 is equal to this squared, SK2. And what that means, if G is large, okay, so this holds always, but if you found that this G constant is large, like the geometry definition between the classical ML and the quantum ML differs greatly, then you would always have, and you can always find a data set such that SC is much larger than SQ, which means that for that data set, your quantum ML would predict more accurately than classical ML, which implies a prediction advantage using that quantum ML. So concluding all of the these things that we discussed, we came up with this flow chart to understand like sort of the opportunity where you will see some kind of quantum prediction advantage. So basically, first you go through the geometric test. You try to check if this G constant is small or large. If you found that it's small, then you know that classical ML will predict similar or better than the quantum ML. So you just throw that quantum ML away. You probably don't want to use it. But if you found that G is large, it always means there exists some data set such that you will see a prediction advantage. However, for a particular data set that you're interested in, you still have to look at this SC constant. If you found that SC is small for the classical ML, then you know that classical ML would do well, then you probably also don't want to use quantum. But if you found that SC is large and then SQ is small, then you know there is the potential quantum advantage. Yeah. So that's sort of the idea here. And one thing to note is that using this, you can start thinking about what this quantum kernel method are doing. And as we have said in the illustrative example, if you found that if you place your quantum states, like if you place your classical input in a quantum Hilbert space that's very high dimensional, what will happen is that it's going to predict that, which is kind of counterintuitive because you would usually expect that when I use this kind of supervised learning using quantum feature space, you want it to be able to place your classical input in a large Hilbert space. Otherwise, if you place it in a small Hilbert space, that's classically simulable. However, the fact is that when you just do that, you place it in a large Hilbert space, what would happen is that they would be kind of too far apart, and you will not be able to predict well. Of course, there's also another condition, is that this observable has a small Frobenius norm, which means that this observable itself is like a low rank projector. In that case, that's also good. But oftentimes, like if you just wanted to be able to predict some local observable or like some thermodynamic quantity, this observable O would have a very large Frobenius norm. Because note that kind of like all these, like let's say it's a local observable, so it's like Z tensor a bunch of identity. If you square it, and then it becomes a bunch of identity, and you take the trace of it, that would be 2 to the n. So oftentimes this trace O square is actually very large. And that's also what we observe in a large scale experiment that compares classical ML with quantum kernel methods. And we found that actually classical ML performs better than this quantum ML in predicting like the output of quantum neural networks. So one solution that we came up with is this following idea, where you don't just work in this exponentially large. Yeah.
Sorry, could you go back to one slide above? Yeah. Okay. So what you say here is that because your original quantum kernel is when your Hilbert space is large and you have like a bunch of input and output. So basically, what it gives to you is the identity, right?
It would be quite close to identity, yes, because everything are too far apart.
And then
although it would not.
Yeah. And then
it's not really cool.
And then when I plug that into the equation of geometric difference, it would give me roughly 1.
Yes.
Because the K is identity.
It's near identity, yes.
Okay.
It's not just equal. There are still a lot of fluctuations around because things could still be close then. But it would be close to identity. It would be close to 1, the geometric difference. And recall that we have this proof. So you know that S is less than equal to some small number times the quantum model. And it would just fail the geometric test. And you know that classical ML would predict similar or better than the quantum ML.
And also when I try to calculate this quantity S using this kernel, because the S depends on either the dimension of your input or like the trace of it, the trace of the O square.
Yes.
Okay, so usually the trace of O square is, we can ignore it if we like, we use like local observable and it's like a large Hilbert space.
Yes.
So the only bound to this quantity S is the dimension of your input, and that can also be large if you use this form. Okay.
And that's going to be causing problem. And actually, you could prove rigorously that there are some very simple quantum model where when you train this quantum ML method based on quantum kernel, it requires at least exponential number of data. On the other hand, the classical ML only need linear amount of data to do it. So there are quite some, these are some caveat that's become more evident after we did this theoretical analysis. So one solution that we use which is kind of counterintuitive, is you don't just work in the quantum Hilbert space. You don't define everything using the inner product in the original quantum Hilbert space, but let's say you project your quantum state back to some classical representation. For example, you could use this method called classical shadow that to project it back to some classical representation, and you define your kernel. It's still a quantum kernel because you have to go through this process. You embed it into quantum Hilbert space, you project it back to some classical representation, and then you define a kernel in this classical space, which seems like originally you might feel like, oh, now you're projecting everything back to a classical space, then do you still get an advantage? It's actually yes. By doing this step, it's actually much easier to prove advantage than quantum kernel method. So what I mean by that is, like here, we discussed like the prediction error for quantum kernel method, and there's actually a very recent paper called A Rigorous and Robust Quantum Speedup that basically tells you that training quantum kernel method would have some quantum advantage if you assume some cryptographic assumption. But their proof was kind of hard because quantum kernel method was very hard to work with. There's a lot of limitation in what it could learn, especially like this trace O squared. So they ended up constructing a very intricate and a very brilliant kind of a feature mapping such that the corresponding observable could be like rank 1, and then you could predict well. However, if you just do this, like you map it into a quantum Hilbert space, you project it back to a classical representation, define everything in the classical space. So basically you're just using you're still using the quantum computer. So you still get some quantum power out of it, and you do that, then you actually ended up increasing the geometric difference. So in our numerical experiments, we found that quantum kernel often have small geometric difference, but by projecting it back to a classical space, what happened is that now everything are not so far apart. So in the Hilbert space, everything is too far apart, and that's why the geometric difference was small. But when you project everything back, everything becomes close again. And then this actually increases the geometric difference. And yeah, it also results in a very simple, like kind of like a one-page proof for a rigorous quantum advantage using this projected version. So now let's just quickly go through the numerical experiment. So we focused on this data set called Fashion MNIST.
So Robert, like so basically you you provide like this quantum advantage under what kind of assumption? Like
this problem is the same as what they did. Basically just saying that discrete log is hard classically.
Okay.
So it's not super. Yeah, that's why it's only like one-page proof. It's pretty straightforward. So just assume that discrete log is hard, and then basically what it's doing is it's trying to learn some learning problem built on discrete log. So now for the experiment, we focus on Fashion MNIST. This is a much newer data set. It's also very widely used data set. And the reason people consider this is because MNIST is too simple and everyone uses it. So for example, people found that you just need a single pixel, like you randomly select a few pixels, and then you could train a model that solves MNIST very well, which is not great. So Fashion MNIST is a harder version of that, which is basically like giving an image, detect if it's a dress or it's a shirt or it's a shoes. In particular, we focus on a binary classification task where we wanted to give it an image, predict if it's a dress or a shirt. And here we consider what we did is we try to embed this image into a quantum state using some technique that people have already proposed. So this is more like just using some of the things that people have already did and just try to check if there's quantum advantage and how we could improve upon that. So here what we do is we first map each image into an n-dimensional vector where n is the system size. And then we consider different embedding strategy. So actually I only consider 3, so it should not be 4. The first one is you just separately rotate your qubit, like in different qubit, you rotate it. And the second embedding is this IQP circuit that was created by the IBM, they proposed by the IBM people in the supervised learning in the feature space paper published on Nature last year, where you have like a layer of Hadamard, and then you have this kind of IQP circuit that's a rotation, like add some phase into the model, and you have another layer of Hadamard, and then you add some phase into the model. And then the third embedding strategy is we just take this Xi and make it into like the interaction for some for a Heisenberg model, and then we just evolve it for some period of time to embed your classical vector into the quantum state space. And in addition to this data set, we also consider another very synthetic quantum kind of data set where we just throw away the original label. We take in the image, we embed it into the quantum state space using these 3 different embedding strategy, and then we evolve it using a random 2D Heisenberg evolution. And after that, we measure some local Z operator. So now in this task, it would no longer be a classification task like predicting dresses or shirts. Now it's kind of like I have an image. I just take it and I evolve it through some quantum evolution, and then I wanted to predict what the output is. So this is a sort of a more stilted data set that we wanted to consider and to showcase some of the theory that we proved. So, and furthermore, we also consider the following classical ML methods. Here's a list of them, quite a variety of common models that people use. And we spend a lot of time tuning all the parameters, and we report the best model. So now here is the experiment result. So in the most left-hand side, this is for different system size. What's the dimension? What's the dimension that you placed your input into what's the effective quantum Hilbert space dimension that you put your classical input into? And the different lines, like this red one, orange one, and blue ones, they correspond to different embedding using the quantum kernel method. And this dashed line are the projected quantum kernel method. So from here, you can easily see that for quantum kernel method, because you just throw it into this quantum Hilbert space, the dimension grows very quickly. So the blue one, which is the separating rotation one, doesn't grow as much, but like the Heisenberg evolution one or the IQP circuit, both have like very quick growth in the dimension. On the other hand, because for projected quantum kernel, what we do is we put it into the quantum Hilbert space, but then we map it back, so the dimension is much smaller. It's like this. However, on the contrary, we could also look at the geometric difference. So then you can easily see that for the original quantum kernel method, even though you place it in a very large Hilbert space, and that's actually exactly a problem. You place it in a very large dimension Hilbert space, and what it ended up is that the geometric difference with classical ML is actually very small. So especially for large system size. So we consider, here we consider a system size up to like 28. And you can see that while for a small system size, the geometric difference could be large, for large system size, it quickly goes down, or it slowly goes down. On the other hand, when you do the projection back to the classical space, noted as the projected quantum kernel, you found that the geometric difference is much larger than its corresponding quantum kernel. Like the geometry of, if you just place it in the quantum Hilbert space, the geometric difference with the classical ML is much smaller than when you map it back to a classical space. And this could be seen, like the theorem that we showed before, it could all be seen in plot B, which shows the prediction performance for 4 different data sets. Dataset C is the classical dataset, and this dataset Q, E1, E2, and E3 corresponds to the same experiment, just with a different embedding. So like we have 3 different embedding, and how you embed it would actually create a different data set, and that's the 3 of them. And
Just
what you could, yeah.
Quick question. So when you upload the data into the quantum system, do you upload it like only once, or do you do this like trick of re-uploading as well?
Sorry,
when you upload your data into the quantum system, like those 3 embeddings, do you like upload the data in there like for 1x is like only once, or like you do this like multiple times of uploading the data as well?
You mean for a same input x?
Yeah.
For E1, I would upload it using the E1 embedding. For E2, I would upload it again using a different embedding, and E3 is another one. Is that the question?
No. Let's go to like E1 for example. Like go to the like Okay. So let's say that you want to upload this x1, x2, x3, right? That's like 3 features of your one input. When you upload the data into this, you put it in the x rotation.
Yes.
You put it only like once, like x1, x2, x3, and then that's it, or you put like x1 like multiple times as well?
Oh, yeah, it's just x1, x2, and x3, and that's one state. But actually, when you run it, you have to run it multiple times to get the expectation value and stuff like that. Right. I hope that answers the question.
So the question was about the re-uploading of the data, and the answer I think it's no, right? You just do it once. There's no re-uploading.
Yeah, I don't think but we do have there's no re-uploading, but we do have to repeat the same experiment for several times.
Of course.
Okay. Thank you so much.
No problem. So here you can see that like whenever the geometric difference becomes very small, you will not see much advantage. So for example, like when you compare quantum kernel, when you look at quantum kernel method, this blue, yellow, and red one, you see that so the lower the better. So this is prediction error. All 4 of them are prediction error. So the lower the better. The green dots are the best classical ML. And you can see that best classical MLs always perform similarly like here, or actually outperforms the quantum kernel method in predicting output from Heisenberg evolution, which is, but that's also expected, as we have shown in the previous theorem. Whenever you have a small geometric difference, you will not see quantum advantage, and actually you might even perform worse than classical method. However, like for example, here you see that projected quantum kernel method has a large geometric difference, like for the pink one and the blue one. Then there is a potential for quantum advantage, but it might not be there. It's possible that for the data set you consider, they're not there. However, when we look at this data set QE2 and QE3, we both see that there is some slight advantage over the best classical ML. Of course, this doesn't mean that it would have an advantage over all possible efficient classical ML. It's just these a wide range of ML, like common ML models that we tried. Right. And furthermore, as we have said, when you have a large geometric difference, you could always construct a data set that saturates this sk1 less than equal to g squared sk2. And you can do it like experimentally, and that's what we do here. So basically, we compute the geometric difference g, and then we construct a data set that saturate the inequality that's shown here. So we try to saturate, we can explicitly construct a data set that saturate this. Like there exists, and it's actually explicitly constructible. And that's what we do here. So for the first one, we consider projected quantum kernel using the first embedding, the rotation embedding. And you see that for the first rotation embedding, the geometric difference is the smallest. And what that means is even if you construct that data set, that specialized data set, you will still not see too much advantage. So the green ones are the classical ML, while the blue ones are the projected quantum ML. And I have 2 different system size, training set size. like training set of 100 or training set of size 600. So when you increase the training set, it always increases. However, when the geometric difference G is small, you will not see advantage even in this particular data set. However, when you consider the third embedding, which has the largest geometric difference, for this particular data set that saturate this geometric difference inequality, you can see that there's a very significant amount of prediction advantage comparing the projected quantum kernel method and the best classical ML model. So yeah, so kind of to end it with a more positive viewpoint, BQP is still larger than P/Pauli, hence any classical ML with data. So to conclude, we talk about how data could provide computational power that enables classical ML to be slightly stronger than one would originally expect. And we showed that actually classical ML could also solve some quantum problem, could also learn some quantum problems that might actually be hard to compute without the training data. However, quantum ML should still be stronger than classical ML. So quantum advantage in prediction accuracy is definitely possible, I think. But even though we have conducted this large-scale experiment to verify this, I think more investigation, both theoretically and experimentally, are needed to justify an actual like a quantum supremacy for machine learning problems. So that's it. Thank you so much.
Beautiful. Thanks, Robert. Like it was a quite neat and like awesome talk. So I think there have been already a few questions, but I think we can still take a couple of questions from the audience. And if you have a question, just like just unmute like as you were doing, like, and ask the question to Robert.
I will have one. I'm very sorry to hijack the thing. I asked so many questions.
No problem. Not at all.
So first of all, thanks for the talk. It's amazing work and really nice talk. I really appreciate what you all did, guys. Okay, so there's this this idea of projection and the idea of constructing the data set. So for the projection, just naively, it seems a bit like, okay, I get it. You end up with this a bit negative conclusion. You want to find a solution to it. But it seems like, okay, now we're taking those data, we put it in this huge Hilbert space. The problem is that everything is too far, and then we're projecting back. It seems like taking a long route to say, okay, quantum can give something, because at the end we project. So it seems that we could find maybe a straight way to this projected kernel classically. So naively,
you mean
yes? So
going from classical ML to projected quantum kernel, just completely classically?
Yeah. So my question at this stage is like, do you have a sense of like, why is it good to do this intermediate step of going in this very large Hilbert space, other than it's classically hard to do? Do you think that there's actually a fundamental reason why we gain from it? Because we're taking this long route that might not be necessary.
You mean, so I think you might have are you I guess you're not asking, but are you asking like, does there even exist one task that you would benefit from it, or you're asking in general, why do you benefit?
Yeah, I think in general, not one task, more like in general, like it seems that we're going in this large Hilbert space, but you figured out that, oh, that's a problem because everything is far apart. So the kernel trick is difficult. So let's project back. So, but then when you look at the final result that you are projected, it seems that, okay, maybe we should not have gone to this large Hilbert space, and then maybe we could do this mapping straight away, classically or more efficiently.
I see.
It's an open question. Like what's your take on it? It's more like
So I think the following might make sense. Like, for example, you wanted to be able to predict certain outcomes of certain molecule, like for example, I'm just talking out loud, in the far future, like you wanted to use quantum computer or quantum ML to like design drugs or design new materials and stuff like that. I think it's possible. Like, I think what would be nice is maybe you try to embed some description of your material into the quantum space, and then you do some evolution there, and then you extract some properties out of the evolution done on your quantum computer, and that's sort of the resulting projected description of your original molecule. So kind of like you have a molecule, and then you go through all these long routes to create another set of like properties, a new set of features, properties of your original molecule that enables you to predict more efficiently. I think that might be possible. So
Okay.
I hope that.
Yeah, okay. And very quickly, with the constructed, so am I right to just understand that at the end when you constructed those data set is like, okay, let's see the best case scenario. Let's construct that and see in which cases the distance is the worst, is the largest, but in practice we randomly pick them, so this is not something that we should expect.
Yes. Okay. So that is the one that actually maximizes this that saturates the separation, but in practice you
randomly
probably see it's less than. So SK1 would be less than rather than equal to. So the advantage would definitely be smaller than this. So
thank you again. Thank you for your patience of all my questions.
No problem. No problem.
Yeah, I mean, thanks, Mark, for asking nice questions. So I think since it's already 11:30 in Singapore, and it might be already late for Robert also, like.
It's okay. It's just 7:30.
Yeah. Okay. So let's once more thanks Robert. Like, I mean, thanks Robert for like giving such a nice talk, and like so this closes the session, and see you guys again in later sessions.